Okay, next we're going to talk about the number E. Actually, I need to scroll up a little bit so you can see this part in the notes. So the number E, this is an irrational number, and I'm going to sort of talk you through why this number is important and why we're going to be where it comes from. You should know that for the most part, I'm not going to hold you responsible for understanding this sort of limit idea that we're going to be talking about today, but it's important to just not feel like it's coming out of nowhere. So back in some point in your life, maybe in geometry class, you learned about this irrational number called pi. We know what it means to be irrational means we can't write pi as a ratio of two integers. So pi, you most likely learned about when you were talking about taking the circumference of the circle and dividing it by the diameter. So if you take that ratio, now this is not a ratio of integers, of course, but that ratio gives you this constant pi. And we approximate pi to be 3.1415, and then it just keeps going. So we know we can't, if we're looking at the decimal expansion, it's infinite and it never repeats and it goes on forever. So today we're going to look at another sort of famous irrational number, which is E. It has a value of approximately 2.718. And so for the sake of most of the things we're going to work with, if you just think of it as a number about the size of 2.7, then you're going to be fine. But I want to just let you know how this number arises. So one common application of exponential functions are interest problems. And so interest problems would be things like you have some finite amount of money, you invest it in a bank account, the bank account gives you a certain amount of interest on that, and then you ask questions like how much money will you have after 3 years, or when will you have $10,000, or you ask questions about that. These are these interest problems. The most common form that you would probably have seen in the past is this thing right here, this A equals P 1 plus R to the T. So if that's not familiar to you, then you can learn about it now. So what does that mean? And this is going to be a little messy here, but A is the amount of money you have after time has passed. P is your principal amount of money invested. R, and sorry I'm going all over the place here, but R is your interest rate written as a decimal. So that's that same R that we talked about in class last time. In fact, this 1 plus R is that exact same base, right? I talked about that being the base. B is 1 plus R. So that's exactly the same as what we were talking about last time. And T is just our variable because rather than talking about the variable being X, it's an interest. So our independent variable is time. So we just use a time. And notice that the variable is in the exponent. So this is exponential. So this is the sort of most basic interest kind of problems. I'm writing it in function notation here. So the only difference here is trying to make this look more like the sort of parent functions we were talking about yesterday. Yeah, I guess this was yesterday. So yesterday we had some A and then B to the X, or in this case, B to the T. So I'm showing you that these interest problems with just changing the letters are really just exponential functions like we just talked about last class. The B is 1 plus R. Instead of having a y-intercept calling it A, we can call that y-intercept, or our P is our initial amount of money. So this is all just letter changes, but it's the same thing. So, right, and it says it here. A is the initial balance, so that's like your principal amount invested. R is your percentage as a decimal, and T is time. So all of this is in here. Okay, so now this formula will tell us the amount of money we have after a given amount of time. So for example, the problem we did in class yesterday was if we have $1 with a 100% interest rate, which would be awesome, we get the doubling function. F of t equals, we really have a 1 here. Our A is 1 times 2 to the t. So that's from our first example. So after 1 year, when t is measured in years, we see that we have f of 1, which is 2 to the 1, which equals $2. So the problem we were doing actually last time in class, I think we said t was measured in days. So that's just a matter of what units we're calling it. So now we're going back to years, but it doesn't matter. We just have to specify what the units are. So it looks like here I said years. So this formula assumes that we calculate the interest only once per year. In other words, the other way of saying that in sort of fancy way is that the money is compounded annually, which means annually we compound our money, or we compute how much interest we earn. Now, that's not ideal because, of course, you don't want to have to wait a full year before you earn any interest. And so for that reason, we want to compound our money more frequently. I believe banks do it Every day, daily, at the end of the day, you can check your balance and you've earned some money. So we have this slightly fancier formula for that. So A is still the initial amount of money, or you might have thought of this as P, your initial amount of money. R is still your rate as a decimal, but we have this new variable N that shows up twice in the formula. And notice that this N times T in the numerator, you might want to think of that as being, I'm not in the numerator, I'm sorry, in the exponent. You might want to think of that as being in parentheses so that you remember that that product is all in the exponent together. So this new variable, this N, stands for the number of compounds, the number of times we compound per year, or per whatever the units happen to be. Usually it's going to be year. So the number of compounds per year. So where N is the number of times compounded annually. Oh, so there it is, written in much nicer print. But okay, so and again, I show you that this is the same thing as the formula you may have seen in some other math class. So let's look at an example. So if we compound monthly, that would be N equals 12. So I'm going to just scroll up so we can see both pages here. Oops, a little too far. Oops, way too far. I'm on a different page now. What's happened? Hold on, stand by for a second. You can see all the work we did on the last video. Okay, so if we compound monthly, N is going to equal 12. And so again, starting with that problem, like let's assume we start with $1. So A is 1 in here. Our R is, we have 100% interest rate, and so that tells us that R is 1. And if we compound monthly, so N is 12, this is the formula we would get. So after 1 year, if we wanted to know, instead of having $2 at the end of a year with only one compounding, what happens if we compound 12 times? Well, f of 1 is going to give us, instead of $2, about $2.61. So we see that compounding monthly gives us 61 more cents at the end of the year. So that's a little bit more money, and what we'll see is the more frequently we compound, the more money we earn. This should make sense because if every day you earn some interest, or every, so the next example is going to be daily. If you continue to earn more interest, then not only are you going to earn more money sooner, but you're going to earn money on the interest you've already earned. So you're sort of earning interest on your interest. And so it compounds, which is exactly why that word's coming from. So, for example, if we compound daily, so if N is 365, then after 1 year, we see just doing the same exact thing. A is 1. We still have the same scenario where we're taking our $1, investing it into the bank, but compounding 365 days a year, we get 2.71. So another 10 more cents by compounding daily. And we can continue this compounding more and more frequently until eventually the equation represents what we call continuous compounding. So in other words, if we take the limit, so I'm looking right here, if we take the limit as N goes to infinity, so think about this number and this number up here, this compounding, that going towards infinity, we get the expression 1 plus R over N to the N. Now, using calculus techniques, we can show that this limit as N goes to infinity, with this being an R here in general, goes to the expression e to the R power. So if we let our compounding go to continuous, instead of having, I'll just remind you of the other one, it was A 1 plus R over N to the NT power. Okay, all of, let's see if I can change, so the 1 plus R over N to the N power, all of that is being replaced with e to the R, and you can see that in fact that's what we get, A e to the R t. And so we have this thing called continuous compounding, and when we use continuous compounding we have the base e. Notice that e has an value, so just as we're about to say right here, so we can define this irrational number e to be this limit as N goes to infinity, and as we saw in the example with the $1, it was 2.61, then 2.71. And if you were to go until N goes to infinity, we get a decimal approximation of 2.71828, etc. It goes on. And so this base of the exponential function, which we're calling e, is called the natural base. And that's where this number e comes from. It's coming from this limit right here as N goes to infinity. And you can think about it as, in terms of interest problems, as approaching a continuous compounding. Now it says, as it says in the packet, if you got a little lost in this last paragraph, don't give up. Oh, why do I keep skipping pages? Okay, I'm not sure if I was just recording that time. Hopefully that was paused. Okay, I think I just wasted a lot of your time. Sorry. So, okay, so like I said, if you got a little lost in that paragraph, the upshot really is that you want to be thinking about e as a number between 2 and 3. So when you think about the bases, we know that for bases greater than 1, exponential functions are going to be increasing, and certainly e, which is about 2.718, is greater than 1. And so the function e to the x has exponential increase, and it looks roughly like this. Okay, and now I'm going to stop here until the next video.